So, in this part of the first lecture, we will be discussing the Newtonian mechanics of a system of particles. Let's say instead of one single particle, we now have a system of capital N number of particles, and their mass, position and velocity, they are respectively denoted by mi, ri and vi. Of course, ri and vi, they are defined with respect to some specified origin, and this index I ranges from 1 to capital N. The total mass moment of the system is then defined by the sum over I, mi, ri vector, where the mass moment of a single particle is simply the mass of that particle times its instantaneous position vector. Okay. Now if we define another position vector which is given just simply by this ratio of the total mass moment of the system to the total mass of the system and is denoted by capital R, then this is known as the famous center of mass of the system. So center of mass is nothing but a position, okay, which may or may not be occupied by a real particle of the system. Okay, but if we think that the total mass of the system would have been concentrated at that position, then the representative mass moment of that position would be simply equal to the total real mass moment of the system. Okay. Now if we define another reference frame or frame of reference, taking the center of mass position as its origin, then we can easily say that the origin is actually situated now at R, and if the position of ith particle in this new CM frame or the center of mass frame is denoted by Ri prime, then Ri prime would be simply given by Ri minus capital R. Okay. Then we are just multiplying both sides with mi and having the sum over I, we can simply say that this is equal to summation over so actually this summation over mi ri prime is equal to summation over mi ri minus capital R times summation over mi, and by definition of center of mass this is 0. So that simply says that the total mass moments of the system with respect to the center of mass, okay, that means or you can just say that the total mass moment in the center of mass frame of the system of particle vanishes. Okay, this is another way of defining center of mass. So center of mass of a system is such a point about which the total mass moment of the system vanishes. Okay. We can also write this like m capital R is equal to summation over mi ri. Then taking the total time derivative of the both sides, you can say m capital R dot is equal to summation over I small mi small ri dot. Okay, what is this? This is nothing but the total linear momentum of the system, and that is equal to capital M R dot, capital R dot. So another way of saying this is the total linear momentum of the system of particles is equal to the linear momentum of the CM. Of course, we are assuming that some imaginary particle equal to the particle having a mass equal to the total mass of the system is situated at the center of mass position. Okay. Then simply another corollary of this total mass moment with respect to the center of mass vanishes simply gives that the total linear momentum with respect to the center of mass also vanishes. Okay, that is nothing but the time derivative of this equation number 2. Then again from equation number 3, which is this, we get mr double dot is equal to summation over I small mi small r I double dot, and which is the by Newton's law is the total force. Okay, so the resultant force acts on the CM of a system of particle. So what is the real meaning of this? This means that we can always think in an equivalent manner that the total resultant force which is really acting on the system can be thought to be a representative force which is acting on the center of mass position, and always the assumption is that some imaginary particle having the total mass of the system is situating there. Okay, so basically r double dot is the acceleration of that imaginary particle. Okay, now in general, if there is no real particle over there, basically you cannot simply see that somewhere some particle is really accelerating as this at this position, right? So this is nothing but an equivalence or an equivalent picture to simplify the analysis. Which is really useful in several cases. Okay. Now here you can see that then you can say that m, that the total mass times the acceleration of the center of mass is equal to the total force, and which is the total which is the sum of all the forces, okay, acting on the particles. So it is a sum over I of Fi, where Fi is the total force on ith particle. Now that force can be decomposed into two parts. Remember, one is external force, that means some agent which is exerting the force is totally outside of this system of n particles, and then there is the internal force which is coming due to the interaction of the ith particle with the all other particles of this n particle system. Okay. Now that one, this Fi internal, can be written as a summation over j not equal to I. Of course, the self force is assumed to be 0. Fji, here my convention is like this. So F given by jth particle on ith particle. This is in some book you can see the inverse, but you can use any of the two, but you have to be consistent throughout with your convention. Okay, so follow one single convention. Then if you have this, you can always write m capital V dot is equal to this. Okay, so this is the total external force, and this is the, so I can write this. So this is the total external force, and this is the total internal force. Okay. Now, by Newton's third law, you know that the internal forces of action reaction between ith and jth particle, they're equal and opposite, right? And then specifically, if you just see this expression, and if you, for example, if you expand really taking any n, let's say 3 or 4 or 5, whatever you choose, and if you expand that, this is a very nice homework, you can see that you will always have like terms if ji, if you will have, let's say, if you just take n is equal to 4, then you just you can have equation like terms in a couples. Okay, couples of this internal force contributions, where you can see like F12, F21, F32, F23, this type of terms. And due to this equal and opposite nature of the action reaction forces, they actually counterbalance each other. I like strongly suggest you to do this at home, like taking, let's say, for n is equal to 4. Okay, capital N is equal to 4. Then what will be the summation? You will see that you will have all like even number of terms, and they will be written in couples. Okay, and they will vanish each other, or they will cancel each other rather. Okay, and finally you will be given by this one, that mv dot is equal to this summation over I Fi external, which is nothing but the total external force. So the acceleration of the center of mass is only due to the external force or the total external force. So internal forces cannot accelerate the center of mass. Okay. Now, if the total external force vanishes, although there are internal forces of action and reaction, the total linear momentum of a system, which is mv, capital M times capital V, is zero, because this is then linear momentum is constant because this is zero, right? And then we can actually recover the PCLM, or the principle of conservation of linear momentum, for a system of particles. Okay. Now what happens for the angular momentum for a system of particles? Now the total angular momentum we have to define. This is nothing but the vectorial sum of the angular momentum of individual particles. Okay. And they are simply given by this vectorial vector product of Ri cross Mi Vi, okay, and summation over I. Then again we can write, in order to simplify, you will see how this simplifies the total calculation. We write the every position vector in terms of the center of the coordinate of the center of mass, or the position vector of the center of mass, plus the position vector of the ith particle in the center of mass frame. Okay, if you write that, and then also if you develop the velocity vector also as a sum of the velocity of the center of mass frame and the velocity of ith particle in the center of mass, okay, the velocity of the center of mass position plus the velocity of ith particle at the in the center of mass frame, then you can finally expand the whole thing. Here you can see the detailed calculation, okay, the whole thing into 4 terms, where you can have this summation over I Ri prime cross Mi small Vi plus summation over I Mi small Ri prime cross capital V should be independent of the summation, okay, then plus capital R cross summation over I small Mi Vi prime plus capital R cross capital M capital V. Now by definition of the center of mass frame, the total mass moment and the total linear momentum of the system in that frame vanishes. Both of them vanish. So that's why we are left with 2 terms. So the L is equal to R cross MV capital M capital V plus summation over I Ri prime, that should be a vector product and not a plus. This is an error, okay, yes, cross Mi Vi prime. So the total angular momentum of the system will be the vector sum of the angular momentum of the center of mass itself, always assuming the total mass is concentrated at the center of mass, plus the angular momentum of all the individual particles about the center of mass, that means in the center of mass frame. Okay, please correct this one. This is a cross sign. Okay, now a question comes, can you express, similar to the above method, the kinetic energy of a system of particles? That's you to do at home. Okay, now let's have a look at how the EL changes, total EL changes with respect to time, and that will simply give us the torque of the system. See, if we do the calculation, you know that there will be a term which is coming like summation over I Vi cross Mi Vi, which will vanish, and we will be simply given with this part, which is summation over I Ri cross Mi Vi dot, which is again the total force. So the cross product of the position of the ith particle with the total force acting on the ith particle, and finally taking a summation over I of all such cross products. Okay, then you decompose again the total force into 2 parts, external and internal. Now you write, so the external part will simply give you the external torque. There is no problem with this. And for this internal part, actually you have something to understand. If you now write this, so basically there are two sums, but this sum is now on both Ri cross the summed quantity of IFJI. If you do that, again I suggest you to do this for n is equal to 3 or 4 to check at home. You can see that you can always write it in a way such that if you make an ordering that I should be less than j or j should be greater than, j should be less than I, then basically this expression will be equivalent to writing a summation over, this is a double summation over I and j, okay, Ri cross Fji plus Rj cross Fij. If you don't put this constraint, basically this will, if you just do this double summation I and j over this whole quantity, you will see exactly that will be twice of this quantity. That means you will have every term appearing twice. You just check and get convinced. Okay, this is not a big deal. This is very trivial home task. Okay. Then finally, by using Newton's third law, you can say that this one is minus of this one. So finally you are given with, for this summation, of course, a double summation of I and j, I less than j, we are taking one order, of course, yeah, okay. And this is nothing but Ri minus Rj cross Fji. Okay. Now, how to comment on that? So one easier way to say that if this force is parallel to this one, that means if the reaction force, action reaction forces between the ith and jth particle, these are all acting along the line joining these two particles, that means they are central in nature, then only you can say definitively this vanishes. Okay. And you finally have, for those type of systems, you have dl dt is equal to simply the external torque. So the rate of change of total angular momentum about the origin is equal to the net external torque acting on the system about the origin, of course given for the case of central internal forces. Okay. If the internal forces are not central in nature, then this is not a guarantee. Okay. Now again, so if T external is 0, finally you can say that L is a constant of motion. Okay. And we have the total angular momentum for a system of particle is conserved. Finally, we have a look at the total mechanical energy, which is capital E, for the system of particles. And here we first decompose from our knowledge the total energy into three parts. One is the kinetic energy, total kinetic energy of the particles, individual particles, okay, which is the summation over I half mi vi square, plus this is the total potential energy due to the external force field, and this is the potential energy due to internal action reaction type of forces, okay, interaction force. Now the question is that as you know that here the basic assumption is, of course, that all the forces are conservative in nature. Now what happens if the forces are non-conservative in nature? We know in general that the energy is not conserved, and how to do the analysis you can have a look on your own, okay, and let me know what you find. But here I am just doing it for conservative forces where these potential energies are basically defined. And again, starting from Newton's second law, you can write the total force into two parts, external and internal. Then just taking the like the mi ri double dot, just taking for the considering the ith particle and contracting this with ri dot, okay, you simply say that this is equal to half ddt of mi vi square. or ddt of half mi vi square. So this is nothing but the rate of change of the kinetic energy for the ith particle. Okay, this mi ri, this one. Oh, okay. So this, yeah, mi ri double dot dot ri dot. Okay. And fi external is written as usual minus gradient of I. So this is for ith particle vi external, and that part you can always write against in the similar way as above. Okay, contracting with ri dot, you can write this is equal to minus gradient I vi external dot ddt of ri. And if you just do this do this calculation carefully, you will see this is nothing but the total time derivative of the scalar function vi external. For internal force, again we have to for the simplification of the analysis, we have to suppose that the force is central in nature, and this Vji, this is a function of Rij, that is only the distance between the relative distance between the ith and jth particle, and the same for Vij. Okay, as we all know that Rji and Rij, they are the same. So you can see that Vji is equal to Vij. Okay. Now next we have this term. We have to simplify this term. Rather, we have to try to write this in terms of the corresponding potential energy. And we will see again, as we did for the case of the calculation of the torque, this is either you write as a double summation by specifying order, that is I less than j or I greater than j, or you don't put any constraint on the order, but you simply say this is equal to half of this double sum. Again, you can check that at home. Okay, this is equivalent by saying half over here, or you just saying I less than j or I greater than j. Okay, any of them is correct. Then if you write this, you will be given by this expression, and this expression finally give you the minus ddt of Vji. Remember, Vji is a function of Rij. Okay, it's a distance, so which is nothing but the mod of Ri minus Rj, right? So in some sense, a Vji should be a function of both Ri and Rj, and also you can think that if Vji doesn't have any explicit time dependence, then if you just expand ddt of Vji, you will simply be left with this expression. Okay, so basically I suggest you to start from this expression and go into this expression. That's easier, okay, to understand. Okay, then you can see that if you take now the double sum of over this type of quantities, finally you will be given you will be left with this expression, minus half summation over I and j ddt of Vji. Now taking this half and those two sums, okay, which are commuting with ddt, of course, you can write the whole expression is to be equivalent to minus ddt of V internal, where V internal is a representative of the total the representative of the total potential energy due to internal forces, and which is simply equal to half summation over I and j Vji. Now combining C, this is the equation C, with summed up A and B over I, we finally get, so this was B and this was A, we finally get this expression, ddt of the total kinetic energy of the particles will be simply equal to minus ddt of the summation over Vi external minus ddt of summation over I Vi internal. Okay, so as you can see that here finally we can write this maybe I am just trying to be more clear, because here you can see this I wrote this is total V internal with this double summation. Here I have just written VI internal. So VI internal is just taking into account the one single sum over J, where when this is also summed over I, you will be simply given as V internal. Okay. So here for ith particle, the total potential energy due to interaction with all the other particles than ith particle itself is given by Vi internal. Okay, and then you can see that the ddt of the total quantity is 0, and this is the total energy of the system, and this is the conservation of mechanical energy for a system of n particles. Remember, in this conservation we have assumed so many things. Okay, several assumptions. Okay, one is that the force should be conservative in nature. Another is the potential function should be independent of the time. Another is the interaction forces should be internal, reaction action forces should be central in nature. So all these things are there. Now think, this is you as a brain twister I am just giving, like to this is you to think now. Think what will happen if the internal forces are not central in nature. They are conservative, but they are not central in nature. Then how to proceed? Okay, think and search. Okay, these are some problem you can think of your own without asking me the further answers. But if you find something, then you can come and suggest me, sir, is this the correct way to go, or is this the correct answer, or this. Okay. Okay. So that's all about the first lecture. So of course, in the next week we will be coming back to all these dynamical properties in a different framework, which is the framework of Lagrangian and Hamiltonian, which is a very, analytically very useful formalism for classical mechanics. Okay, thank you very much.